Good afternoon, everyone. Thanks for joining us. Today, we'll be talking about how we can hack our accounts at integration platforms with a new class of authorization attacks. I am Kai-Xuan Luo, a PhD candidate at the Chinese University of Hong Kong. And I started this work when I was a former intern at Samsung Research America. So this is a joint work with my lab mate, Chen Bo, who's standing next to me, my PhD advisor, Professor Lau, and my colleagues and managers at Samsung, Adonis and Julian. This is our today's agenda. We'll start with an executive summary to get it warmed up with the basics, and then go through the attacks with detailed protocol analysis. We'll share with you the result of our investigation against 20+ integration platforms with concrete attack examples. So first of all, what is an integration platform? In a narrow sense, people often refer to it as workflow automation platforms, such as Microsoft Power Automate or IFTTT. But here we're also including several other types of platforms that has a similar architecture, including virtual voice assistants such as Alexa, smart homes, for example, Google Homes, and most recently, large language model platforms with plug-in support, like OpenAI ChatGPT. The commonality between these platforms is that they all wish to build an all-in-one solution that will connect and aggregate the functionalities of diverse apps or services on the internet. For example, you can ask Alexa to turn off your smart bulbs and then get a ride with Lyft to the airport. But in this example, since you are communicating through Alexa, the Lyft server must somehow figure out which Lyft account is requesting the ride. So that's how account linking comes into play. Account linking is a must-have feature supported by all integration platforms, which will link the end user's app accounts to their platform accounts, so that the platform can therefore control the apps on behalf of the end user. And to establish account linking, OAuth is the most prevalent protocol being used. Integration platforms have a marketplace to accommodate all its apps. This is usually an open marketplace where anyone can register and publish an app. So keep in mind that the third-party apps could be inherently untrusted, and there could even be the infiltration of a malicious app. In account linking, normally a user just links their own app account, like Lyft account, to their platform account, like Alexa account. So it's perfectly fine, and nothing can go wrong. However, let's say I am an attacker and you are the victim. If I can somehow steal your Lyft account and then bind it to my Alexa, then I can request a ride for free, and you're going to pay my bill. So this will cause unauthorized access. On the other hand, if I, as an attacker, can unknowingly bind my Lyft account to your Alexa account, then I can track your traces whenever you request a ride in the future. So these impacts could be realized with the attacker's presence as a malicious app, targeting a benign app, and refer to it as the cross-app attack scenario. Then some platforms may have an impression that, well, let's just close our marketplace and make sure that there's not a single malicious entity involved. But that's not a panacea. It turns out that an attacker could still act as a normal platform user and target a victim directly, also launching unauthorized control. So we refer to this scenario as the cross-user attack scenario. So cross-app and cross-user attacks will be our focus today. To give you a better understanding of what kind of attack we are able to launch, here's an example. The left-hand side is the attacker's phone, and the right-hand side is the victim's. They're all running Alexa. And there's a victim's smart lamp, which could be controlled with victim's Alexa. So now victim is tricked to click on a single link. And he is already doomed because an attacker actually just hijacked his account. Now the attacker can control the victim's smart lamp with their own Alexa. So that's quite simple, but also quite scary, isn't it? So next, we'll go into the technical details. We'll go through the protocol flow and highlight how the OAuth protocol can be abused in account linking. Under the hood, account linking is based on the OAuth 2.0 authorization code grant. This actually coincides with the traditional OAuth use case where the authorization can be granted to the OAuth client. So it's a 3-legged protocol done in 2 phases. There are 3 entities involved. The first entity is called the OAuth client, which is usually hosted by the platform backend. There's a platform frontend, being the user agent. Usually it's in a web browser. And each integrated app would host its authorization server. It's done in 2 phases, and the first phase is the authorization phase. Eventually, a short-lived authorization code will be issued. And to begin with, the end user would initiate account linking from the platform frontend, which would start the underlying OAuth flow, and then hit the integration platform backend. Then the user would be redirected to the integrated app's authorization server like this. The user would usually be asked to log in at the app's website and then grant the authorizations. But please note that although it is named authorize, the authorize button or any user consent can usually be skipped if there's a prior consent. So this would make the authorization process fully automatic, and the authorization code will be issued without any user interactions. So the authorization code will pass through the user agent and be handed in to the platform backend. It will hit the redirection endpoint. This is labeled as R here. And this endpoint, where the URL is specified earlier through the redirect URI parameter. So that wraps up the first phase. The second phase is the so-called token exchange phase. So the authorization code will be redeemed for an access token through a purely server-to-server communication. So eventually, the access token indicating the app account's access will be associated with the platform account. And from now on, the platform could call the app's APIs with the access token attached to control the app on the user's behalf. If you're familiar with OAuth security, you might be aware that there are 2 common types of attacks. First one is about the redirect URI. If the redirect URI is not matched against by the authorization server, then the authorization code could have been leaked to an unintended server. There's also a state parameter in OAuth, which tracks the OAuth states and then also used as the CSRF cross-site request forgery token. So if the state is not correctly bound or matched against, it could end up with a login CSRF attack. But since we like to explore those new security challenges in account linking, we assume that the platforms and the apps are all exempt from these common flaws, or at least our attacks do not depend on these flaws. So account linking is based on OAuth, but it does not equate with OAuth. Account linking, there are some unique challenges for account linking that requires further customizations to the OAuth protocol. Specifically, the platform needs to coherently track the active app and the active platform user information, or in other words, to maintain an account linking session during account linking. And failure to do so would expose session integrity issues and break account linking. So next, we will go through these issues one by one. We'll first start with the issues related to our cross-app attacks. In traditional OAuth, there is only just one authorization server involved. But in integration platforms, it needs to support multiple integrated apps or services, where each app has its own authorization server and their own account linking needs. So first, the platform needs to support linking with both Lyft and Spotify like this in separate OAuth flows. But more importantly, in order to achieve this, the platform must remember the user's choice in the first place, and then later retrieve it. Why is the case? Because as OAuth involves 2 phases, for the second phase, the token exchange phase, the platform needs to send the authorization code to the exact same app where it initially gets the authorization code from. So the platform literally needs to first embed its initial contact and then later extract this information before the token exchange. And we call this the active app tracking. There are two common patterns to accomplish this goal. The first mechanism is through the state parameter, because state is traveled along the authorization phase. So the platform could embed an app identifier, say Lyft, in the state parameter and assign it to make sure that nobody can tamper it. That's one way to track the app ID. Another choice is to embed the ID in the redirect URI, like in the URL path, so that the platform could also extract this information when the user agent hits the redirection endpoint. However, it turns out that these information alone are all insufficient from a security standpoint. Why? Because, say, for state parameter, it only reflects how OAuth is started, but it cannot track how OAuth is ended up with. The state is opaque to the authorization servers, so the state could actually be traveled along the OAuth flow to multiple authorization servers, but the platform and the authorizations would know nothing about it. And this oversight can result in an attack that render account takeovers, and it goes like this. First, just to make sure that we're on the same page, we assume here that the platform is tracking the active app solely by the state parameter. So let's say when a victim stumbles upon a malicious app for account linking, the platform would embed the malicious app's identifier in the state parameter and then take the victim to the malicious app server. But instead of authorizing the user as what it's supposed to do, the malicious app's authorization server would issue a crafted redirect to another benign app's authorization server. From the benign app's perspective, everything looks legit, so it will be the benign app who issue an authorization code. But the redirect would also keep the malicious app state, such that when the state is sent together with the authorization code back to the redirection endpoint, the platform would retrieve the active app information from the state and think that, well, I've been always communicating with the malicious app. So then the platform would send the authorization code of the victim to the malicious app server. And once the authorization code is leaked, that's basically endgame, because the attacker just needs to launch a vanilla authorization code injection attack, which is well discussed by the community, and to redeem the code for an access token and then bind the token to the attacker's own platform account. Because this is essentially stealing the victim's app account, we named this attack cross-app OAuth account takeover, or COAT. So the second common design, as we've mentioned, is to track the active app through the redirect URI parameter, but this is flawed as well. The reason is that the redirect URI by itself has weak integrity, so it can be changed by the attacker, say from Lyft to Spotify. So based on this idea, we could launch a different attack that enables privacy leakage. The attack would also begin with the victim starting account linking with a malicious app, but because the redirect URI lacks integrity protection, the attacker could change the active app from malicious app to benign app like this. So what's the purpose? It would make the platform later contact back to the benign app for token exchange, like this. So the attacker could actually leverage this app context switch and inject a still valid authorization code of its own and into the OAuth flow. And that's how an attacker could inject their own app account at the benign app to be forcefully linked with the victim. We call this attack cross-app OAuth request forgery, or CORF. So the root cause of both problems is that the platform would solely rely on the state parameter or the redirect URI for the active app tracking. So to defend against these two attacks, our solution is that the platform should first embed the same app identifier in both state parameter and the video URI, and then extract it from both to see if they're consistent before the token exchange. Why would it be an effective approach? Because in this way, if there is a code or crypt attack going on, the state parameter would indicate a malicious app's identity, but the video URI would indicate a benign app. So now the app mismatch would make the attack sensible by the platform. So now I've finished the cross-app part, and I'll hand over the presentation to Symbol to talk about the cross-user attack.
OK, thank you. Thanks for Kaixuan for his introduction and also on the cross-app attack part. Now I'm introducing the cross-user attacks. So before that, let's first again take a look at this classic OAuth flow diagram. But this time, you can just ignore all those arrows and all the parameters inside. You can just focus on the red part in the diagram, which is the user session on the platform. Note that the session is actually not part of the OAuth standards, but it plays an important role in account linking. The account linking is initiated from the platform by the user, and then finally, after OAuth authorization, the platform will rely on the session memorized in the user agent to tell which user to authorize to. In simple cases where there's only one browser and one platform domain, this can be very easy. All you need to do is to rely on the browser to manage the session cookie automatically. However, the assumption that the user agent can keep track of the session may break in some other more complex scenarios. So this is the first scenario where it can become challenging to manage, to track session. In this case, you can see that the server, the left-hand side, the same platform may have multiple different domains, or we can call it origin. So in this case, the user will first initiate the account linking from alexa.com, for example, and then after all the authorization information will finally goes to Amazon.com, which will be in charge of all the account management stuffs. So this is a common practice for big platforms for reasons like server-side decoupling. The problem here is that the browser cookie cannot be shared across different websites under different domains, so that Amazon.com, who received the authorization, knows nothing about which user to link to without an session. So one common implementation pattern we observe in practice is to add another round of redirection between the two different domains. So the session information can be carried from one to the other. Just look at the middle, the orange part. The pre-authorized URL with the session ID, which have the session variable in the URL, is how some of the platform pass the session from origin A to origin B. When a server adds the second origin, or origin B receives URL, it will set the corresponding cookie in the browser to mark the so-called account linking session, a session that can tell the platform to link to which user and which target app. So can anyone spot the vulnerability here? Just take a look at the middle part. Do any of the an ancient attack called session fixation attack come into your memory? So because the server only relies on the URL here to dispatch the cookie, the attacker can just send the pre-authorized URL with the session ID inside to the victim. And then victim click the link, and all the OAuth magics happens just in a blink. And finally, the attacker's platform account will get access to the victim's app account. Well, who can expect such an almost forgotten attack still exists in many big platforms, and it just hides itself in the OAuth protocol in some other form. And another scenario which brings the challenge for session tracking is when the native app is involved. Imagine that you are using Alexa mobile app, and then you initiate the account linking inside the mobile app, and it needs to pop up the external browser to request the authorization from some app's website. So the external browser has no information about the platform session in the native app, because there's no easy way to pass a session or cookie from the native app to the browser, for example, from Android mobile app to the Android system browser. So here we have two user agents which will break the session tracking. Implementation we observe in practice for this case is to reuse the state parameter in OAuth to embed the platform session. By design, the state parameter is for memorizing any custom information through the OAuth flow. So it is a natural choice for platform developer to save the session inside it. This time, although it's not very obvious, it is once again vulnerable to session fixation. So the attacker can just send the authorized URL circled in the diagram to the victim and let victim finish all the OAuth stuff. And then attacker, again, his platform account can get unauthorized control to the victim's app. So to summarize, this kind of problems happen all because of the actual OAuth process happen on an unauthorized space in the right part of the diagram, separated from the original authenticated space. And platforms usually will add some mechanism in between to pass the session from one to the other. And it's very easy to make mistakes here, which will lead to the session fixation attacks we just mentioned. Our recommended fix is to make the protocol always return to the original user agent who have the initial session information. And it can either be the native app, or in the first case, it will be the initial domain who keeps the session. In that way, the session passing is no longer needed. And yet, the platform can still know which user to link to after OAuth. OK, so that concludes all of the attacks, both the cross-user attack and cross-app attack. Then I will pass back to Kai-Xuan for the rest of the presentation.
So after realizing all of these attack vectors, here are some of our initiatives to heal the internet and make it a better place. We investigated 25 integration platforms of different categories, including 7 workflow automation platforms, 6 virtual voice assistants, 4 smart homes, 2 LLM-based plugins, and 6 other uncategorized platforms. There are all major players in each category, and many platforms has over 100 million users. As a summary, 24 out of 25 of them are vulnerable, and 19 platforms actually support attacks that can be completed in a single click on an unassuming link. If we break down the 2 categories of attacks, there would be 16 vulnerable to cross-app and another 16 vulnerable to cross-user attacks. And there are 8 platforms overlap. As our responsible disclosure efforts, we've informed all 24 vulnerable platforms, which has been confirmed by 16 platforms. We have accumulated 4 critical or P1 bugs, and the most critical CVE assigned has a CVSS score of 9.6. We also received some generous bug bounties. Especially kudos to the following responsible companies. Samsung for first studying these issues as early as 2019 and later extended to this full-blown research. We want to thank Microsoft for keeping us closest in the loop, Amazon for responsibly fixing these issues and also always been generous in bounties, and Google for fixing these issues in 2 weeks. So next, let's move to a concrete case study. To begin with, here's another quick demo. This time, the victim, still, it's lured to click on a link. But what the attacker could do now is that it could view all of the victim's Microsoft Outlook emails. So this attack can actually be launched against Microsoft Power Automate. Normally, you could automate workflows there, like sending you a Gmail whenever a new GitHub issue is filed. But here, we are actually not attacking those third parties, but Microsoft-owned first-party apps. They are implicitly trusted, so actually no user consent from the victim is ever needed. Also, the victim user does not even need to be a Microsoft platform user or like need to be aware of the existence of this platform. The victim only needs to have a regular Microsoft.com session in his browser to get compromised. And this is because here we are actually combining the cross-app and cross-user attacks. For session fixation or the cross-user attacks, it is the attacker starting account linking with a benign app. But unfortunately, Microsoft platform is not directly vulnerable to that. The Microsoft platform indeed has a code vulnerability, but usually to exploit code, it is the victim who proactively contact the malicious app for account linking. So that means the attacker needs to first at least publish the app into the public marketplace of the platform. But here, by combining the two, it is actually the attacker starting account linking with an unpublished malicious app lying in their own developer console and only asking the victim to complete the account linking. And that could achieve first single-click account takeovers. So for the attack details part, to start with, the attacker would register such a malicious app in his own developer console. But instead of publishing the app, the attacker simply initiates account linking on his own. And then it will generate a URL dispatched account linking session in a pre-authorized request. Then the attacker could distribute the URL to the victim and trick him to make a click. The victim will be redirected to the malicious app's authorization server, and then the malicious app server, operated by the attacker on the left-hand side, could be programmed to launch the crafted redirect in the cross-app account takeover or code attack. So this would redirect the victim to a benign app server, such as that of an Office 365 Outlook, the Outlook app on Microsoft Power Automate. But notice that in this crafted redirect, the malicious app state is still there, and it will be used later. Normally, if you just link with Microsoft first-party products, there would still be an account selection page like this, although technically speaking, it is not a consent screen. But actually, this this account selection page could also be bypassed if the attacker just tweaked this URL parameter in the crafted redirect. So therefore, an authorization code would be issued automatically without the victim noticing about it, and it would just hit the redirection endpoint. Since there is a code vulnerability at Microsoft's site, so although we can see that in the redirect URI, the app ID indicates that of Office 365 Outlook, of a benign app, the platform would still solely determine the active app by the app ID in the state parameter, which is the malicious app. So the platform would just send the victim's Outlook authorization code to the attacker, and that's how the authorization code is leaked to an attacker-controlled server. And after that, the attacker could just exchange the code for an access token and then bind it to their own platform account. You may notice that here that like Microsoft do have a user session integrity check. And it is meant to check whether there is an attacker's account linking session that's happening at the victim's browser. And that's why Microsoft is not directly vulnerable to session fixation issues. However, this check is way too late that the token exchange actually precedes it. So the authorization code is already leaked with a code attack by the time the platform could realize that something actually goes wrong. So Microsoft actually fixed this bug in 2 steps. First, it makes sure that the user session integrity check is done in a timely manner, and then it fixed the code vulnerability by always mandating and then matching the app ID in video URI and the state parameter. Eventually, the attacker could just simply put up a workflow and to use the stolen Outlook account of the victim, like forwarding all the victim's emails to his own server. With the same attack technique, we could even leak more confidential data, like this. We could leak the API keys or the secrets from the key management service of Azure, the so-called Azure Key Vault. So now we assume that the victim is actually a vault admin. And again, the victim is tricked to click on a few links in a crafted email. And now all of the key names in the victim's key vault are available to the attacker. The attacker chose one of them, and now the secret value is there. So it turns out that an attacker can steal your Outlook emails, leak your Azure secrets, and also compromise 50-plus Microsoft services in 365 in Azure. These are the related work of our research. In particular, we'd like to highlight that account linking integration platform is an emerging use case for OAuth. So it brings forward a paradigm shift in OAuth roles and trust relationships. So the authorization servers, which are usually trusted entities in traditional OAuth, are now taken up by the untrusted apps. And this is what makes our cross-app attacks lethally practical. This is a summary of our research. We inspect 25 mainstream integration platforms and found 32 instances of vulnerabilities. So these attacks could lead to unauthorized access or privacy leakage, and we have also proposed respective defenses for all of these flaws. We want to end our talk with some key takeaways. First, account linking in integration platforms has critical design flaws. We have done our jobs to secure those mainstream platforms, but we believe there could be more platforms out there that are still exploitable in the wild, including leading to single-click account takeovers. We name our work "One Hack to Rule Them All" because, first, the impact is actually everywhere. It is pervasive across all well-known brands and covers almost the entire internet. And all apps or services integrated within these vulnerable platforms are actually impacted. Moreover, it should be the platform's responsibility to fix these issues. But until a platform actually takes some action, all users, including you, could be victims. Lastly, there's still an urgent need for industrial standards to secure the entire ecosystem, because in that way, future platforms would be securely introducing their account linking mechanism from day one. Thank you, and I'd like to welcome our contributors also on stage, and we are ready to take questions.
I have a question. So for the Power Automate implementation, when you did the actual attacks across, we're using the same tenant or an attacker tenant to do the actual execution of the attack?
Yeah, so actually, the victim and the attacker could belong to different tenants. Yeah. And to launch the attack, Yeah, it's just like the attacker could be in any tenant. It could be like the attacker don't know the victim before, and it's done like in completely isolated environment.
Sure. So I've been using these attacks since like 2018. I have some of my own research on how to automate, very similar to this, different from the attacks, but what's interesting if you are targeting a O365 Microsoft environment and use your own attacker tenant, the same security controls do not apply to your tenant that should apply to theirs, although you're using their own OAuth tokens. So the interesting thing is you can actually disable that functionality. In other words, disable the ability to have an attacker put your tokens into their tenant. It's called tenant isolation. So it actually prevents that attack entirely across the platform. So that's one mitigation that's really effective for this.
Yeah, thank you for sharing.
Yeah, thanks.
Any other questions? If there's a question, you can come to the mic.
Thank you very much for providing a really good example of that interdependency and weakness. What about automations such as hyper-automation platforms that are available at more of the enterprise level and popular even in the business hall booths today? Can you comment on that?
Yeah, I would say like you could view Microsoft Power Automate as both a consumer-facing and an enterprise-facing platforms. And actually, if you talk about the workflow automation platforms as a whole, those enterprise-facing platforms are usually called IPaaS, or Integration Platform as a Service. And we also found a few cases, like in our evaluation, maybe 3 or 4 of the 7 vulnerable workflow automation platforms are actually those enterprise-facing ones. Yeah. So they are, I would say, like consumer and enterprise-facing platforms are equally vulnerable.
Okay, if there's no more questions, that's it. And you can welcome to chat with us offline. We'll be here for some time. Okay, thank you. Thank you all.
Thank you.